All right, welcome everybody to Not at Lunch. It's my pleasure to introduce Jesse Frohlich. Did I say that right? Is it k or ch at the end?
Um, K.
K, Frohlich. All right, and he will speak to us about From Tangles to Links. Take it away, Jesse.
Thank you. Let's just do this quickly. Excellent. Okay. Um, Welcome everyone. There we go. So today I'm going to be talking about a little taste of my research, or at least the avenues of math leading up to it. So yeah, the project I've been working on is, um, in its simplest description, finding a particularly pleasant knot invariant. So ideally, a knot invariant should have a few properties that make it, both informative and easy to work with. So some of the properties are that it is a good knot invariant should be able to distinguish between knots well, knots and links. I think most people here have heard of the tricoloring number, which is easy to compute, but fails miserably at this property. Another area is that we want the knot invariance to be computable in a reasonable amount of time. And reasonable in this case means computable in some polynomial time with respect to the number of crossings. Yeah, and with a constraint like this makes it more reasonable for computing on large knots, ideally for the sake of verifying some sorts of conjectures that are out there. And thirdly, we would hope that this invariant is able to work well with and detect topological properties of the knot. So more than just distinguishing whether two knots are equivalent or a knot is trivial, we would also like to have an invariant that can understand properties of knots, or be able to be computed on part of a knot in two different ways and then glued together in some meaningful way. Be able to detect when we, double a strand in a knot. Properties like this make the invariant easier to work with and more well behaved. So this is the background for the specific invariant that we're looking at. So yeah, what I'm going to jump into next is the background for a knot invariant like this. So this was developed by both Dror and Roland van der Veen, who is, I think, several time zones over that it can be difficult to attend the seminar. So let's start with talking about the algebraic context for this invariant. So who here has heard of Hopf algebras before or worked with them? Okay, all right, a reasonable chunk of people. This is great. Then we can.
I wouldn't say I'm very comfortable with them, but I've heard of them, if that helps.
Okay, so the impression I get is some level of comfort, and for others, maybe just wet feet. So yes, let's go through some of these details. So a Hopf algebra is several things, but I guess we'll start with a Hopf algebra is an algebra. So by this I mean an associative unital algebra. Which I believe everyone has seen before. Matrix algebras are a great example, or at least square matrices. Group algebras, universal enveloping algebras of Lie algebras. These are all vector spaces with a multiplication. So this is all we have written here. We have some we have some vector space. There we go. And we want some multiplication map on it. And we also want a unit. And so normally we think of the unit as some element of the algebra, such that for all elements of the algebra, we want 1 times a to be equal to a times 1 to a. Another way of thinking of an element of an algebra is just by taking a map from the base field. So this field here, if you want, I think for this talk, it'll basically be the rational numbers, but if you prefer complex numbers, go ahead. So then this map eta, it is uniquely determined by its image on the number 1, if it's going to be multiplicative. So eta of 1, we could define this to be the 1 in the algebra, and then we know that eta of r is going to be r times eta of 1, which is just 1. So all this to say, we can conceive of the element 1 as a map from the base field into our algebra. And this allows us to write the axioms of an algebra diagrammatically. So here on the left, we have associativity. So looking at the 2 different ways of multiplying 3 elements, we could either multiply the 2 on the left and then multiply them together, or we could multiply the 2 on the right and then multiply the remaining result. So these 2 paths here would correspond to the 2 ways of multiplying 3 elements. So this diagram commuting is the same as the associativity axiom. And then over here on the right, we have the same thing for the unit axiom, which I wrote here, but this is it in diagrammatic form. So adding a factor which only has the number 1 and then multiplying by 1 should be the same as the identity. Are there any questions so far? Excellent. Okay, so the next several slides will be basically this repeated over and over with slight variations, which you might call tedious, but I would say is an excellent testament to the symmetry of Hopf algebras. So an Hopf algebra is an algebra. It is also a co-algebra.
Jesse,
Wow.
I'm really sorry. Before you go on, I'm just a little bit confused about the unit map. You said that for any r, the map of r is equal to r times the map of 1 is equal to the units.
Oh.
Wait. So does that imply everything goes to 1, or?
I'm sorry, you have made an excellent point. Yes, this should be r times the unit.
Okay, so then is there a difference between the identity map and this map that you're mentioning?
Right, so this map here, one way to think of it as, so the domain and codomain are different. Right? In one case, we have a field. In the other case, we have an algebra. You could think of this as embedding the base field into the algebra as a subalgebra.
Okay.
In the case of matrices, this would send the rational numbers into diagonal elements.
Okay.
Or multiples of the identity matrix.
Okay.
Yeah,
okay.
Cases.
Gotcha.
Yeah, sorry, I missed the scalar there. Okay, so Hopf algebras both have an algebra structure and a co-algebra structure. And the reason I wrote those axioms in terms of diagrams instead of the standard algebraic way is because describing coalgebras becomes absurdly easy. All I had to do was put co in front of everything and then reverse every arrow. And at the very least, come up with different names so we don't get too confused. So the co-multiplication map will write with the symbol delta. You can think of it, it starts with delta, so some mnemonics you can think of are the diagonal map or the doubling map. Here's a mnemonic that doesn't even start with D. But we could also think of multiplication takes two numbers and multiplies them into a single one. And the co-multiplication you can think of it as splitting it up into factors or simply taking in a single element and giving you two. Depending on which algebra we're working with, some of these analogies will work better or worse. And then similarly, we have a co-unit map. Instead of embedding the base field into the algebra, we map the algebra down to the base field. And some of you may notice this as the trivial representation. So it turns out that a co-algebra structure, this is actually equivalent to an algebra structure on the representations of A, which is kind of cool. You can, this co-multiplication tells us how to multiply or how the algebra should act on the tensor product of two algebras. This is a bit of an aside, so let's not dwell too long, but there's a lot going on with this algebra. It's rather nifty, I must say. And then we have
just about the co-unit. I'm having a hard time understanding what such a map could look like. Like I understand how you can take your like coefficient ring and shove it inside the algebra, but how you go back, is it usually like some sort of evaluation or something, or
usually an evaluate what cases is it? Yeah, you could think of it as like evaluation at 0.
Or like if I think about matrices, what is a map? What is this map in matrix mind? Is it like a trace or something?
It's not quite a trace.
So, I mean, matrices are not a coalgebra, or at least you have to say how they are a coalgebra.
Mm-hmm.
So maybe the appropriate answer is to wait until we have an example, right? I mean,
yeah.
Fair enough.
Quite soon, I'll go through a few examples of Hopf algebras. Yeah, I guess the teaser until 2 minutes in the future is that often the map collapses a lot of structure. So it's either, and when thinking in terms of representation theory, it usually ends up being, or it'll end up being a trivial representation. So most elements get sent to 1 or 0.
Jesse?
Yes.
So the right diagram, the left map, do you treat as a multiplication? I was expecting K in the
sorry, which mapping here?
The left arrow going up.
This one? Yeah.
Is that multiplication?
No. So how this map works is, this is a good point. This is a little odd. So what we do is we can interpret this top left factor. We can interpret as the base field tensored with the algebra. insertion of scalars doesn't actually, or the isomorphism is clear enough that I've actually omitted it in this case. And then here the co-unit takes the left factor and collapses it, and then does nothing to the right factor. Does that help?
Yeah, thanks.
Cool. Yeah, and then this arrow on the top means that we're reinterpreting A on the left as A with K tensor on the right. Yeah. Great. So now we have the Hopf algebra, we have the algebra structure, we have the co-algebra structure. So our next task is to see how well they play together. So this is where bi-algebras come in. So the bi-algebra structure, we want both an algebra and a co-algebra, and we want them to play well with each other. So to play well with each other, I have this rather convoluted diagram. It's nice to have commutative diagrams, and this will come in handy. But this is actually equivalent to just saying that the co-multiplication map is a morphism of algebras. Nothing super exciting there, except that the co-multiplication is a map from the algebra to the algebra tensor itself, which means that we need a way of multiplying elements of this vector space. And so we'll do some component-wise. So A tensor B times C tensor D will just be AC tensor BD. So that's what we mean by this arrow on the right, is we swap these two components just as the B and C are swapped. So that's all that's going on here. So we want the co-algebra and the algebra structure to behave well with each other. And then, so that's a bi-algebra. And then the final condition to be a Hopf algebra. And so I'm lying a little bit, so let's add a little bit of truth back. There we go. So above the pink dashed line is a bi-algebra, and to be a Hopf algebra, we have the last condition, which is an antipode. So an antipode is a map which you should interpret as acting like the inverse, but in a more categorical context. So we have this diagram here on the left, which you can interpret as the inverse map. So G times G inverse equals the identity. If you interpret this as the diagonal map, then this would take an element G to G times G. And then if we apply the antipode to one element, then we can interpret this as G tensor G inverse. And then the multiplication map simply multiplies these two to just the element 1. And then on the bottom, this is just trying to get us the number 1. So we take G. In the group context, the trivial representation sends G to the number 1, and then the unit sends the number 1 to the unit in the algebra. So the pink outline is sort of an intuitive way of interpreting this diagram, but it works in other contexts beyond just groups, which is what makes these so fantastic. Okay. So this is a Hopf algebra. Let's take a look at some examples. So hopefully this will elucidate some of these maps. So let's start with group algebras. So if we have G, a group, I think the easiest way is think of a finite group G. Then the group algebra is just going to be the vector space generated by some list of generators of G, modulo the relations in G. The algebra structure is just going to be the multiplication in the group itself. And then this unit map, I haven't written very, so it takes a scalar and gives you the identity. Maybe I should just write that the unit in the algebra is just the identity of the group. And then the coalgebra structure down below says that the diagonal or the co-multiplication is given by the diagonal map. And when we think of representations of groups, so if G acts on two vector spaces V and W, then we know that G acts on the tensor product. And we know this action is given by acting on both components. And rewriting this as G tensor G dot V tensor W, we see that we can actually interpret this as the co-multiplication applied to G acting on V tensor W. Excuse me. And then similarly, the co-unit would just be the trivial representation. So G acts on the base field by G times so G times R is just R. And then the antipode is just given by group inverse. The next example is going to be relevant for us because this will play a role in building the actual invariant. So if we have a Lie algebra G, we can take the associative unidal algebra to be its universal enveloping algebra. How comfortable is everyone with universal enveloping algebras? Familiar? Haven't seen before?
Familiar.
Okay, a little over the board. So a Lie algebra. Oh, I guess the next question is, maybe I should have asked, what about Lie algebras? All right, I think more experience with Lie algebras. So I think the simplest description of this would just be words in the Lie algebra. So if G is equal to a Lie algebra, is just the span of some generators, then this one is, you could interpret as non-commuting polynomials. In those generators, and then to connect the multiplication of this algebra with the bracket of the Lie algebra, we just add the condition that x bracket y should be equal to the two-letter word xy minus the two-letter word yx. So that we get the bracket and the commutator behave well with each other. In the end, though, this is just an associative unidal algebra related to this Lie algebra. And I've decorated it with some extra symbols because sometimes instead of just taking words or finite sums of words, we want infinite sums, so we can take completions of this algebra. In the end, it's still an algebra, and the multiplication is just concatenation of words or concatenation of these letters. The co-multiplication looks a little different than in the group case. And you'll see that this is how representations of Lie algebras work, where a Lie algebra element acting on V tensor W. This is defined as X tensor, or X acting on V plus X acting on W. All right, so these are a couple examples of Hopf algebras. The next thing we're going to talk about is a concept called a meta-Hopf algebras. Now, this sounds like a lot of suffixes. I just keep throwing at things. Meta-Hopf algebras are not a big leap. Largely, you can think of them as a notational convenience. It turns out they are more useful than just a notational convenience. But let's start by looking at that notation. So far we've talked about algebras and their tensor products as ways of looking at multiple copies of the algebra. So the multiplication map we think of as going from A tensor A to A. And we can write the notation A tensor producted with itself 3 times as a tensor power. But instead of keeping track of the copies of the algebra by what position they're in, so 1, 2, and 3, instead we can label them with elements of a finite set. So that's what we're doing on the right-hand side. Instead of writing the tensor power as a natural number, I'm writing it as a finite set. And by this, I mean take 3 copies of the algebra. These are all identical copies, but I am simply labeling them with elements of this finite set here. And so this allows us to more precisely talk about this multiplication map. Because in the previous notation, if I had A tensor A tensor A, and I wanted to multiply the first and third components together, I don't have a good notation for trying to multiply these two together with a multiplication map and then shoving this over here. Yeah. This diagram here looks like a bit of a mess. Let's find a more clean way of writing this out. So the notation we have written here is that M will take in the 2 copies of A associated with the indices I and J as its input, and as its output on the bottom should provide that result into the copy of A labeled K. And the nifty part about this is this can actually represent more than just this one map. We can also have other indices which aren't affected. I can do something like this. So I can have the set I, J, as well as other indices in the set S. And this will produce an element of A tensor power, the set S union just K. We replace I and J with K. And then here's where things get more than just about indices. Instead of taking an algebra and several tensor powers, all we really care about, right, instead of the Hopf algebra being A, its tensor powers, and then these several maps, multiplication, co-multiplication, unit, co-unit, and the antipode. Well, really, we just care about having sets and maps between those sets. So instead, we could have a collection of sets where S is a finite set. And then we can have all of these maps. So delta will take in a single element and produce 2. The unit produces an element but has no inputs. The co-unit has an input but has no outputs. And the antipode has 1 input and 1 output. And now we can conceive of Hopf algebras, and we can do away with the notion of algebra altogether as well, and instead have collections of sets where A sub S we should think of as S copies of A, where each copy is labeled by some element of S. Right. Is this okay with everyone?
Question for me. Okay, so I'm confused a little bit about the choice of using just a finite set to label the elements. So, like in the example that you did with, we have the 3 copies of A and we want to multiply components from like the first A and the last A, and there's not a good way to do that. So that's why this notation is helpful. But there's sort of like, and maybe this doesn't matter, but in my head, there's sort of like an inherent ordering on the tensor components, like there's an A that comes first, an A that comes second. And I know that probably there's an isomorphism that you can swap the components, so it doesn't really matter what order they're in. But like if I'm just labeling something by a finite set, that does that automatically give me an order? Or does my question make sense?
Yeah, it does. Right, because in the context of, say, monoidal categories, a lot of these isomorphisms you explicitly keep track of. So that is a good point. In the context of these Hopf algebras, the fact that the set 1, 2, 3 is ordered isn't really significant. All that matters is the fact is that 1, 2, and 3 are distinct elements.
Okay, so we really care about, so the ordering, even though like it kind of looks like it's important, it's not actually important, that we don't need it. Or...
Yeah. So the ordering we use only to distinguish the elements, not to determine which goes first.
So like
go second.
When you've written A to the tensor ijk, that could mean AI tensor AJ tensor AK, but it could mean AJ tensor AI tensor AK.
Precisely.
And are those like the same? Are they isomorphic elements or something? Or
so I didn't really specify this, but we are focusing our attention on contexts where the tensor products are naturally isomorphic to any reordering.
Okay.
There are certainly contexts where that isn't the case, but at least for what we've looked at so far with associative unidal algebras with the normal tensor product, that is the case. And so we will use that generously to freely rearrange elements.
Cool. Okay, and one more question. So when you wrote down the sort of new version of the collection of information we need for these Hopf algebras, you said that the like eta has no inputs but has an output. So like you just have an eta sub k. Can you explain that again? I didn't quite catch what that.
Oh yes, sorry. That's so this mij. We can do something similar with the other maps. So we could go eta sub k. This will take in some algebra or some number of copies of the algebra, say S copies, and it will output A with S plus one more copy, and that copy is labeled by K. So in the case where instead of A being an algebra, a tensor S isn't an actual tensor product of algebras, it's simply a set. We could rewrite this as eta k goes from A sub S to A sub S union the element K. And so in particular, when S is empty, we could interpret this map as going from 0 copies of A into 1 copy of A.
And the 0 copies of A is just the base field or something? Or...
Yeah, in the context of algebras, we define the 0th tensor power as just the base field. And very shortly, we'll look at, I haven't actually mentioned knots at all. So very shortly, we'll look at how knots come into play and how we can interpret these sets as topological objects instead of just algebraic ones. Yeah, excellent questions. I'm sometimes steeped in conventions and forget to mention them. Yeah, are there any other questions before we pre-pinned meta to everything? Cool. All right. So now we're going to go back into the other slides, and instead of looking at Hopf algebras, we will look at meta-Hopf algebras and see how things change. Unfortunately, it is not by a lot. Here we go. So now meta-Hopf algebras, we want a meta algebra structure. So instead of the tensor products, we just take the sets associated. So instead of a tensor A, we take the set associated with 2 copies of A, etc. And then these diagrams down below effectively are just a change in notation, where we keep track of indices instead of, if we jump back here, we were keeping track of the order of things. And now we're simply writing down which indices are affected. And then the base field has been replaced with 0 copies of the algebra, or whatever the structures we're working with, the meta algebra. And similarly, we can add the word co everywhere. And now we have meta co-algebras. Yeah, at this point, there's not a lot to explain, except that the prefixes are really piling up. So yeah, now again, we're just dealing with the indices more directly. And then finally, the bi-algebra structure. Yeah, I think the point that Nancy made about caring about the order. So before we had the specific map, which would swap elements so that we could have the AC and the BD multiplied together. Because of the algebra structure on a tensor A. Now these maps aren't necessary because we can simply encode directly which copies of the algebra should be multiplied together in these contexts. So this is the same. This is the same axiom as before, that the co-multiplication must be a multiplicative homomorphism, or a morphism of the algebra structure. But now it's just written in a way that doesn't actually require that these are vector spaces, which is kind of cool.
So just to comment on that. So putting the word meta in front of it, is this actually any different than just a Hopf algebra? We're just using a different notation to describe it? Or is this actually like a new thing? Because it seems to me like we're like, this is just a Hopf algebra. We just kind of found like a clever way to notate it.
Right. The key though is that instead of dealing only with vector spaces and tensor products, we've replaced this with a set. And instead of tensor products, we just have more sets.
And those sets aren't necessarily the powers of the original set.
Yeah, these don't have to be tensor powers. They don't have to be Cartesian powers. You know, all we require is that these axioms hold and that these diagrams commute in a meaningful way.
So A labeled by I and J could be just some rando weird set that's totally different than A labeled by ABC.
Exactly.
Right? Okay. And I assume you're going to show us an example with knots or something.
And I will do so right now.
So
okay. This is a perfect segue. So let's...
I have a question too, sorry.
Oh, yes.
So the set A, I mean, how does it relate to the other sets you have? Are the single index sets equal to A or?
Yeah, perhaps this is a bit misleading. So maybe I should say A labeled with a single index.
And
would
those
be
are
the
all the
closest
same,
analog.
or?
Or they should be isomorphic.
Yeah,
So
okay.
they will have slightly different indices. So yeah, if two finite sets have the same size, then the corresponding A sub S and A sub T, these should be isomorphic to each other
Mm-hmm.
if S and T are the same size.
Okay, great, thanks.
Yeah, so I've sort of neglected the relabeling isomorphisms. All right, so let's jump into an example describing what these sets can possibly be. So on the left, we'll look at these two examples on the left later. All they do is introduce, more convenient notation. On the right-hand side, this new example is the part that's actually significantly different from what we've looked at so far. So A sub S, we will define as open tangles. So tangles with no closed components. And each component is labeled by some element of S. So if you take a look at, say, this component, this picture right here, we would say that this lives in A sub ij. And perhaps instead of A, I should have used VT. But this is, yeah, so now this isn't a vector space in any meaningful sense, but we still have these same operations. And so we can go through the operations to see what this meta Hopf algebra structure looks like for tangles. So the multiplication map, we want to take in strands I and J, and we want to return a single strand K. And so the way we'll do that is, given a diagram that has two strands labeled I and J, we'll join the head of I to the tail of J to form one new strand.
Mm.
And so multiplication becomes gluing strands together. And then co-multiplication should take a single strand and give us two new strands. So in this picture, we have I should become A and B, and we do that by doubling the strand. And
Question. Is it always possible? Maybe this is just a property of tangles, but I'm still working on multiplication. Haven't gotten Como yet. Is it always possible you can connect the head of I to the tail of J without adding any new crossings?
this is an excellent question. So no, it is not.
Okay.
I've cheated here by writing it in a case where it does. So if we do have to introduce new crossings, we simply make them all virtual crossings.
Okay, so you do what you got to do to get there, and then
exactly.
Okay.
Yeah, that's the nice part about prepending virtual, is that it ignores a lot of these physical constraints. So yes, if there were another strand sitting right here, then it would just become a virtual crossing. All right, so, and then similarly with strand doubling, this requires that we have a framing on all of our components. Because depending on how you draw this diagram, the strands may end up twisting around each other. But these are all extra details. This is more of a high level and cursory overview. For the units and co-units, this now corresponds to creation and annihilation of new strands. So the unit in component K just adds a new strand K, which doesn't interact with anything else. And then the co-unit will just delete a strand. And then finally, we have an antipode as well. And this corresponds loosely to taking a strand and reversing its orientation. All right, so now here we have a meta-Hopf algebra structure on tangles. And then we also have meta-Hopf algebra structures on all sorts of our favorite algebraic structures. So this gives us hope that if we can just take a morphism of meta-Hopf algebras from virtual tangles into some particularly well-behaved algebraic structure, which hopefully we know how to compute things in efficiently, this should give us some viable tangle invariant, which is exciting. So let's build this invariant. So the first step we're going to do is look at the algebraic side and build our specific algebra, which will be the target of our invariant. So for this talk, let's just call the algebra, or the Lie algebra, G. So it is generated by 4 elements, y, b, a, and x, and they have some relations. Yeah, you might notice that a and x together form the only 2-dimensional non-abelian Lie algebra. Same with a and y. Regardless, though, it's an algebra. It's a 4-dimensional Lie algebra, and then we'll take words in that algebra, and then we'll complete it. So we have infinite sums of words in this algebra. And the other way to think of this is just to take power series in y, b, a, and x. And then we will define S copies of U to be what we would normally expect is the S tensor power of U. And this is where the notational difference, or this is sort of a notational convenience here. We write, instead of writing y tensor x with y in the ith component and x in the jth component, we can simply write this as y sub I x sub j. So when you see this notation with variables written with subscripts, what we mean is y should be living in the ith component and x should be living in the jth component. A nice part about this notation is it doesn't force us to also add an artificial order to this set. All right, so now we have the target, and we've talked about the tangles. So now let's build the map between these two. So here we have a so we'll define our invariant as this map Z from virtual tangles to this algebra U we defined on the previous slide. And tangles are generated by crossings. So we can write any tangle as a collection of crossings and then stitch all the strands together. So yeah, if we define these two crossings as these two power series, so interpret these exponentials as power series in these terms here, and these are called R matrices. Why is it called an R matrix, you may ask? Well, at least here you notice that these are quadratic terms. And you might complain that this fails to be quadratic. And I would state that you have a good point. And we will sweep that under the rug on another slide. But in the end, we have these two terms. So given a tangle, we can decompose it into crossings, map each crossing to this R matrix, and then multiply all the R matrices together. And this will give us some power series, and this will be the value of the invariant. So some nice properties of this is that because both the source and the target we have interpreted in an algebraic context, we now have the power to take our tangle and split it up into smaller components, compute the invariant on those smaller components, and then stitch them together later. So the invariant and the topological gluing processes behave well with each other. So this is promising topologically. The actual algebra we chose ensures that this invariant is able to distinguish objects well. So the last question we have to deal with is, how efficient is this? And if it is not, then how do we solve this problem?
Jesse, question.
Yeah.
So am I meant to understand that this being a morphism somehow is preserving Reidemeister moves? Or because we're claiming we're getting an invariant, right? And what that means to me is like we preserve Reidemeister moves.
Right.
So is that somehow built in there somehow?
Yeah, so the specific choice of this, the form of these two elements, will causes this to be a not invariant.
Okay, so just as stated, this is just a morphism of these algebraics, but it happens to also be an invariant because of the choice of R.
Oh yeah, this is worded a little funny. So this is a morphism which is also invariant.
Okay, so the Reidemeister moves isn't built into VT or U necessarily. The like satisfying preserving the Reidemeister moves is a property that this map Z satisfies, but
right. So the Reidemeister moves are built into the virtual tangles, right? By sort of we take these diagrams and quotient out by the Reidemeister moves. So the significant part about this statement, which I managed to not write in, so thanks for pointing that out, is that the R matrices also satisfy a condition, the algebraic equivalent of the Reidemeister moves. So yeah, I mean, Reidemeister 2 is just a statement that Rij has an inverse, and this inverse is given by R bar. Yeah, and then the Reidemeister 3 move this on the algebraic side corresponds to the Yang-Baxter equation.
these being R matrices.
Exactly.
That happen, okay.
So yeah, what's significant about these specific power series is that this specific gluing of these R matrices is equivalent to this gluing. Right, so yeah, so here we have an invariant of tangles. It respects the Reidemeister moves. And more than just producing a power series, because we also have these other operations like the strand doubling operation, which is also respected by this map. We get more topological data than just producing a well-defined value for each tangle. So yeah, here's a picture of what a computation would look like. So when we want to compute the invariant on, here we have a one component tangle. We split it up into the various crossings and then keep track of which strands must be glued to each other. And then, well, because this is a homomorphism, Z will respect each of the crossings as well as the multiplications. So we end up with this long string of values in the algebra side. So one thing to notice though is that here we have 3 crossings, and these 3 crossings live in the 6th tensor power of this algebra. And in general, for a k-crossing knot, it'll live in the 2kth tensor power of the algebra. So computations of this sort grow exponentially in the number of crossings. And this can be problematic for the sake of computational efficiency. So here we pull some interesting stunts. So the first one is this bracket relation here is equivalent to ax minus xa. And if we put things to the other side, we see that this bracket relation actually allows us to exchange the order of terms within a word in our algebra here. And so by applying these, and we pay a small penalty, we add an extra term. But by exchanging the order of these terms, we can choose a specific ordering. How about like all the y's go first, then the b's, then the a's, then the x's. And with this specific ordering set, we can actually build an isomorphism, not of algebras, but of vector spaces between this algebra and normal commuting power series in these 4 variables. So the multiplications aren't preserved by this isomorphism. I will emphasize that. But as vector spaces, we can now interpret the algebraic elements just as power series. And so the question becomes, how do we compute maps between power series rings quickly? Speaking of quickly, I will have to go quickly. So I'll mention the Hom tensor adjunction. There are certainly easier ways of saying this. Given a linear map between vector spaces, we can interpret this as an element of a vector space. So there's a correspondence between linear maps and elements of this vector space, where we introduce a dual here. If you haven't seen this, oh, it is so fun. This adjunction comes up everywhere in lots of contexts. It's quite pretty. So this allows us to reinterpret this multiplication map, which is a map between linear spaces. We can interpret as some element of a vector space, namely U dual tensor with itself some number of times, tensor with U. Yeah, and this is effectively taking a linear map and writing it as its exponential generating function. So if you've seen generating functions, this is all we're doing here. And in the previous page, we talked about reinterpreting these algebras as power series. So with this, when we pair a power series ring with its dual, we end up with a pairing that results in this interesting phenomenon here, where evaluating phi, some map between these rings, on some element, so we could write this as evaluation at f. What we do is we replace all the dual variables with differentiation, and then we apply this differential operator to our power series, and then we evaluate at 0. So now the question becomes, how do we compute these differential operators efficiently? And we will go a little faster than hoped, but I think we'll, yeah, let me know. Yeah, so anyway.
Just say you have 3 minutes.
Okay. So let's take a look at the generating functions that we get after going through the procedure on the previous slide. So the multiplication map in the algebra we're looking at, it ends up looking like this. Remember, it lives in the tensor power of some copies of the dual space and some copies of the original space. And this is a bit of a long-winded expression, but it has some key properties that will really simplify the computations. So the first one is, this is an exponential. It is e to some power. And the power has a very specific form. So one thing I didn't mention before, but will now, is that the variables inside this algebra, we bestow them with weights. And the weights in this case have the property that the weight of a variable and its dual must sum to 2, and then the weights are given here. With this weight setup, we see that the weight of A is 2, and so this tells us that the weight of a dual must be 0. The weight of this expression we should actually think of as weight 0 and interpret it as a scalar. And so with this in mind, when we look at this expression, Mij(k) is actually of the form e to some quadratic. This is also called a Gaussian. So multiplication is a Gaussian. And then looking up here at how we define the R matrices, this is also e to some quadratic. And same with this here. So or at least at most quadratic. And I won't go through all of the details because they are many. They're pretty cool though. All these other operations within this algebra are also exponentials of quadratics. And what this means is when we perform our computations, we're only ever keeping track of these quadratic terms. We don't actually have to deal with the entire expression as a whole. So this allows us to reduce our computations to quadratic, plus some bookkeeping. And so instead of the algebra, which becomes exponentially large in the number of crossings, we can now deal with matrices, which will just grow quadratically with the number of crossings. And then plus bookkeeping, it's a little bit bigger than that, but at least now we have a knot invariant or a tangle invariant, which we can compute in polynomial time. The issue though, and in the last minute I will mention this, I've only ever said tangles, and the issue is that we can never actually glue one strand to itself in the framework we've talked about so far. And especially if we want to study links, this would be ideal. So let's take a second and look at matrices. Here's the formula for multiplication of two matrices. So the ikth component of the product of AB, you sum over the product of the coefficients and you pair these two items together. And then when you look at the formula for the trace, it's quite similar, except it almost looks like you're multiplying a matrix by itself. So not squaring it, but just folding it in on itself and collapsing it. And it turns out that this intuition actually holds. So our goal, so what I've been working on now is taking the interpretation for knots, where multiplying two knots stitches them together. And then, what we're hoping for here is some trace on component I would take strand I and glue it to itself. So yeah, my project now is trying to find a formula for a trace on the algebraic side, which fits into this whole framework. And ideally is also a Gaussian. And if it's not a Gaussian, if it's close, and this allows us to still compute it efficiently, then we will actually have a way of computing invariance on links and not just components that only have open, or not just tangles with only open components. So this is one direction we're headed. But yeah, I hope you have learned some things with the project I've been working on, and Jor and Roland have been working on for even longer. Yeah, that's everything. Thank you.
Let's thank Jesse. Are there any questions? I guess I have a little question. So if I'm kind of understanding the procedure is like, okay, we have this way of computing the Z map, which turns virtual tangles into these U algebra guys. And then the trick to computing quickly is to sort of forget that we have a huge algebra structure, but that there's a vector space isomorphism to an easier polynomial thing. And then you can compute the elements faster there than you could back in the big algebra. Is that kind of the right like mind frame?
Yeah. So the idea is that where are we? Yeah, right here. Yeah, the power series that we're working with, because they take such a specific form, all the computations relating to computing these invariants only ever deal with a small subset of our algebra. Mm-hmm. So by reformulating everything in terms of generating functions, we can just work in a small slice of the algebra, or a small slice of the morphisms, rather than all power series. So if we're
trying to think of how to compute elements in this giant algebra, there'd be no hope. But the idea is that we're landing in this very specific type of element, and computing those types, there is this nice, like, efficient way.
Exactly.
Got it.
Yeah.
Cool.
I also have a question about, so at the end you said like there's this issue where you can't glue the thing to itself because of, like, I don't know, there's no trace like this. But if you have a tangle and you want a loop to go back on itself, you need to glue the strand to itself, right? Like, so how is that different from, like, sorry, like,
right. So the framework we've been looking at so far is only, so yeah, when I say tangles, I only mean tangles with open components. Right. So this is allowed, but if you have some component where one of them loops on itself, this framework can't actually compute the value of this.
Right. So I think I'm getting a little confused by what the multiplication is. Like, multiplication, you're gluing different strands together, but like if you want, I don't mean loop back on itself like it completes a circle, but like if you want like a Reidemeister 1 move type of loop on itself, then you want to glue the two ends of the crossing.
Oh, yes. So this we can actually interpret. Yeah, so a Reidemeister 1 move would look like this, right? And so we can actually interpret this as we can start with a tangle with two components, and then we can glue the components together.
Right. Okay. And okay. Right. I see. Yes, thank you.
Yeah. So this would be the R matrix followed by some multiplication. Yeah. So we can do quite a bit in this framework, but the only thing we can't do is close loops, which is somewhat unfortunate.
Only thing you can't do yet.
Exactly.